So this is joint work with Zisin John. You probably never heard of her because she's an undergraduate student. Actually, she's going to start at Berkeley first year as a graduate student in the fall. So let me first tell you a little bit about my motivation. So for a while, I was thinking about this. I was trying to understand spaces of non-negative recurrent metrics on surfaces. Let's consider the simplest surface S2. And I want to understand the space of, let's say, isometry classes of metrics, of C infinity metrics of non-negative curvature on S2. And I want to put a Gromov-Hausdorff topology on it. Now, I cannot really understand this at the moment, but some previous result which I had joined with Taras Banach. So this is sort of looking at a similar space with a stronger topology. So here I'll look at the space of C infinity metrics on S2, and I put CK alpha topology. So here, alpha is between 0 and 1, and k is either an integer, non-negative, or infinity. And so what we do, we determine the homeomorphism type of this space. So this is homeomorphic. We have two cases. If k is infinity, then this is homeomorphic to the countable product of the product of countably many copies of R, the real line. And if k is finite, then this is homeomorphic to the countable product of the space, which is usually called sigma. So sigma, this is a linear span of the Hilbert cube in L2. So just some space. And these two,
with the product topology?
right, the product topology. And these two spaces are different, in case you're wondering. The first one is completely metrizable. It's actually homeomorphic to L2. Second one is not completely metrizable. Anyway, so this homeomorphism is sort of totally unnatural. It's not like I'm introducing some kind of natural coordinates on the space of metrics, but it does allow you to answer certain questions. In particular, if you are interested, for example, one could ask, is the space topologically homogeneous? Are all points the same from a topological point of view? Is the space locally connected? Or what I was thinking about, suppose you take a space and remove some subsets, such as maybe a sphere, topologically embedded sphere. So I'm thinking about deformation of metrics around some obstacles. And then once I know homeomorphism type of the space, it's much easier to answer such questions. Okay, so I would like to have a similar answer here, which I don't have yet. And what I'm going to talk about is sort of a side project in my attempts to answer this kind of question for this space. Now, one certainly has a continuous surjective map from here to here. So this is a continuous and this surjective. And the orbits are also clear. The orbits are just the fibers of the map are the orbits of the diffeomorphism group action pi pullback. So, we have all this isometric metrics in the same orbit. But this is not a quotient map, so this topology is substantially weaker, and that's a problem. Okay? So what I want to have I want to, this I expect will be quite a singular space because it's a quotient. I identify quite a bit. At least it's going to be some kind of maybe. So if you want out here by action of diffeomorphism group, what you expect to get some kind of stratified manifold, stratified infinite-dimensional manifold. What you get here, I'm not yet sure, but the way I want to understand it is I want to realize it as a quotient of some nice space by some nice group action. Oops, sorry. In other words, I'm trying to find a resolution for this singular space. And there is a good natural candidate for this nice space and nice group action I'm about to describe it. So it hinges on a classical result of Alexandrov from the 40s. This is his realization theorem that any metric of non-negative curvature on S2 is isometric to the boundary of a convex body in R3. In the standard R3, and this the convex body is unique up to rigid motion. So you could try to, instead of a nice space, we could try to put the space of convex bodies, and the action is just the isometric group of R3. Okay, that would be an ideal situation, except the main issue is that we are trying to, it's not clear which convex bodies correspond to C infinity metrics. Okay, so the basic question is which convex bodies induce intrinsically smooth metrics on the boundaries. On the boundary. Okay, so it could happen that this isometry in Alexandrov's theorem is just an isometry of metric spaces. It could happen that it's not smooth, it's not an isometric embedding, and in fact it does happen. So this is another classical result of Pogorelov and independently Nierenberg in the 50s. So this isometry is C infinity. So if the metric is C infinity, say, if the metric is, say, C infinity, then the isometry in here is C infinity sort of near the points of positive curvature. Near points of positive curvature. And if the curvature is merely non-negative, then that's not true, that there are some simple counterexamples. And I think the optimal regularity is unknown in general, but I think it's at most C4. So it's certainly not C infinity. Okay, so that's one issue. Now, another issue that I want trying to understand this sort of nice space better, I'd like to say that it's convex. So one has a natural operation on convex bodies, the operation of Minkowski sum, which is the subject of today's talk. So if you have two convex bodies, incidentally, for today, a convex body in Rn is just a compact convex subset in Rn, which has non-empty interior. Okay, and if you have two convex bodies, one can take the convex combination. So one can consider TA plus 1 minus TB, so here A and B are convex bodies, and T is between 0 and 1. And the result is, of course, also a convex body. So this is this set space of all convex bodies in Rn is convex. And if it's convex, then it's sort of easier to try to determine its homeomorphism type. That's the main reason why I care about convexity here, because it really makes it a nicer space. Now, unfortunately, I still don't know which metrics, which bodies correspond to C infinity metrics. Now, and so I just decided to work out this issue for the Minkowski sum. So it could be that you start from two C infinity convex bodies, but the Minkowski sum, the Minkowski linear combination, is not C infinity. That's a possibility. Maybe if you've never thought about it, it may seem surprising, but I will try to convince you today that it's not surprising at all. So let me just remind you, so the Minkowski sum is, of course, just you look at all possible sums. It's a vector sum. And I'm mostly, well, I'll be considering convex bodies which are at least C1. One reason is because this embedding is always a C11 embedding. One can show this. I'm not sure if Alexandrov really showed C11 originally, but it's true, at least for C infinity metrics. So that's the lowest regularity I'd like to think of. And what is known really? About Minkowski, about regularity of the Minkowski sum, and I'll just state a special case. So suppose A and B are C infinity, which means that the boundary is a C infinity submanifold. Then what is known is that A plus B is always C11. So this is a theorem of Kranz and Parks, 92, I believe. And it's not always C2. So need not be C2. So this were the first counterexamples were obtained by Kisselman in 86. So this is when n is 3. And for larger n, this is due to Bowman in 1990, I believe, all right? And also, right, so when I have one case missing when n is 2, and in this case, the situation is a little bit better. So here, A plus B is always C4, but not C5. So this is, again, due to Bowman in the same paper. Now, you may be wondering what's the difference between 2 and higher dimensions. Initially, I planned to explain this, but maybe I have no time. So the basic reason is the following. When you try to determine the smoothness, you're trying to come up with some kind of formula which essentially comes from the implicit function theorem. I'll try to explain it later. And you know, and this formula works under certain assumptions, like, for example, the curvature is positive. And then you try to use the same formula at the points where the curvature is negative, and where the curvature is 0. And this may not work, but in dimension 2, the only way one by one matrix could be singular is when it's identically 0. In higher dimensions, n by n matrix could be singular in many different ways, and that creates more opportunities for discontinuity. So this kind of sort of naive idea, it works up to 4, but then eventually it fails. Okay. All right, so now what is the how shall one think about taking a Minkowski sum of two convex sets? So the picture is very simple. Suppose we have A and B, and you have A plus B here. And you fix a point on the boundary, which is necessarily of the form A plus B. And then it turns out that, well, it's obvious that the corresponding points are boundary points. And so which points are? If you start from here, how do you know which points to take here? The picture is very simple. You draw the tangent line or the tangent plane, and you should use the same tangent plane over here. And that's how you know A and B. Okay. Sometimes it's possible to have a flat face here, and then it's necessarily going to be true that you have some kind of flat face here, or possibly both. Okay. So this is a very simple criteria, beautiful picture how you take a Minkowski sum and determine what happens on the boundary. Now, right. So in terms of the Gauss map, one can try to talk about the Gauss map. So the Gauss map is just of a convex body, is just the outer normal map from the boundary to the sphere. So this is the outer normal. And what I'm saying here is that the Gauss map for A at the point, the outer normal at this point is the same vector. Okay. So now it's good to know that translations certainly do not matter. So we can translate convex bodies, and nothing is going to change. So if you look at A plus B minus A minus B, that's the same as A minus A plus B minus B. So translations are relevant. So we can always translate. So we can assume by translation that A is 0 and B is 0. That sort of makes it a little bit easier to visualize. And so locally, you have this picture. Here you have maybe A, well, dA, and here we have perhaps dB. All right. How should we think of a Minkowski sum locally? So we can, here we have some convex function f and convex function g, and we try to determine the Minkowski sum. Actually, before I do that, I want to, so I said that translations are relevant. What about rotations? So rotations do matter if you rotate one of the summands. Of course, if you rotate them simultaneously, it doesn't matter. But if you rotate one of them, the result could be very different. So this whole project was in part motivated by a question of Mohamed Gomi, who is my colleague at Georgia Tech. And so he asked, can the regularity of the sum be improved by rotating A, by rotating, say, A. Okay. So now this may not be sufficiently motivated at the moment, but I will try to explain why it's a natural question. So the key observation is this. So if, right, so let me just define the Gaussian curvature here. So the Gaussian curvature is just the determinant of the Gauss map. So the product of principal curvatures. And sometimes people put minus here. I don't care. For my purposes, it doesn't matter. So if the Gaussian curvature at A is non-zero, then So if A is ck alpha and B is ck alpha sort of near A and B, respectively, then A plus B is ck alpha at that point, A plus B. And so here k is anything, so it could be an integer, or it could be infinity, or it could be omega. So we can talk about analytic parties, and alpha is also anything from 0 to 1. Actually, I want to start from 2, because otherwise I can't talk about curvature. All right. So this is sort of this is quite basic. I will probably hint how to prove it. It just involves implicit function theorem at the end. Okay. So maybe I should mention that sometimes you get a better regularity. It may happen that A and B are maybe C11 or C2, but the sum is C infinity. And the reason is very simple. When you do implicit function theorem, sometimes you have some kind of unexpected cancellation, and the smoothness improves. Right? So this is not an optimal regularity in general, but that's the best we can hope for, unless there are some special circumstances. So now, assuming this fact, the following set is relevant. So we look at a set which I call ZA, the Gauss image of all points at which the Gaussian curvature vanishes. Okay. So this our convex bodies could have some flat faces in general, but when we apply the Gauss map, every flat face collapses to a point. Just because this set is the set of regular values of the Gauss map, and by Sar's theorem, set of regular values has measure 0. And it's also closed, because this is this is a closed. It's clearly closed, and so this has measure 0. And in particular, it's nowhere dense. Okay. So now another basic observation is that the Gauss map is equivariant under rotations. So if you start from some rotation and apply a rotation to A, this will be the image under the same rotation of the A. Okay. So now here it gives you an idea how to get an optimal regularity, or how to try to get an optimal regularity. It involves trying to rotate this set of the corresponding set for B. So now the question is, or maybe let's just put it as a moral. So if ZA can be rotated of ZB, then R, well, by some rotation R, then RA plus B is ck alpha, assuming that A and B are just like here, ck alpha. Okay, so we have some dense subset of the sphere, of the unit sphere, and we try to rotate it of itself. When can we do that, if we can? This is, of course, a sufficient condition. It's not necessary. So the result could be ck alpha for some other reason. But if it's true, then it works. Okay, any questions so far? Now, from here, one immediately gets the following corollary. So if, say, ZA is countable, then RA plus B and OK. And as always, I'm assuming that my factors are CK alpha, and A and B are CK alpha, where K is at least 2, and alpha is any. Then the Minkowski sum after rotation is going to be CK alpha for any generic R. And by generic, I mean generic in the sense of Baire category. So what I mean precisely is that this, if you look at the set of R's such that RA plus B is CK alpha, the set is co-meager. It's just a short name for the countable intersection of dense open sets. So this is a countable intersection of dense open sets. Okay, so for one, it sort of sells better to talk about generic, but this is what one typically means. All right. So maybe I should remind you a couple of facts of a couple of corollaries from Baire category theorem. So if you have a subset S in SON which is co-meager, which means exactly this, it's a countable intersection of dense open sets, then its complement is not co-meager, is not co-meager, and S is uncountable, and S contains a dense G delta subset. Okay, so in particular, it's dense and uncountable. I should say that the complement could also be dense and uncountable. It's easy to find such examples, but it's not, doesn't contain a dense G delta subset. Okay. So it cannot be that the set and its complement is generic, at least in nice spaces, like in SON and in completely metrizable spaces, and spaces for which the Baire category theorem works. Okay. So this is just a basic. Right, so how do you prove it? The proof is sort of immediate consequence of Baire category theorem. So we have one set which is countable, and another set, in this case, ZB is closed and nowhere dense. So we just need to consider rotation. So we try to rotate one from the other. And the set of bad rotations is a countable union of nowhere dense closed sets. That's all, essentially. Okay, so this is a very basic observation. Now, here's the main theorem which I want to talk about. So this is a theorem when n is 2 for convex bodies on the plane. It's possible to find a convex body A in R2 such that, well, C infinity convex body such. I'm sorry? In R2, right, on the plane. It's all on the plane. Right, so this sort of, I'd like to have similar examples in high dimensions, but I haven't thought about it yet. It should be possible to do it in high dimensions, and you sort of see from the proof the main issue, the main difficulty. So, the conclusion is that you can find a convex body such that if you look at RA plus itself, then this is not C5 for a generic R. Okay. So generically, so we know it's always C4. I think I still have it up there somewhere. It's always C4, but it won't be C5 generically. Now, sort of notice, of course, if R is 1, then you have RA plus A is just 2A, and that's, of course, C infinity. We just scale. Okay? So I chose this example just to emphasize that we have to miss some rotations. So we also, it's easy to construct examples when we have B here instead of A. But our technique cannot ensure that this is not C5 for all rotations. We cannot do that. The best we can do is for generic one, and in this example, it's obvious that we have to miss the identity one. Okay? So now, let me, it's infinity. Right. Yes. It's impossible to make it C omega, incidentally. For analytic, it's not going to work. But C infinity does work. All right, so now let me try to explain the ideas of the proof. So first, I'll try to explain this example of Pullman, where the sum is C4 but not C5. So ours is improvement on that example. So if you think of this local picture, so it's common if you have a function f, the convex body which sits above f is called the epigraph. Okay, and so here we are trying to add two, well, epigraphs of two convex functions, and so it looks like this maybe. So we are adding this and maybe this. And so it will be the epigraph of some convex function. Which function is it? This function is commonly called infimal convolution. So this infimal convolution, and by definition, this is just the infimum, well, at the point x, the infimum of f of x1 plus g of x2, where x1 plus x2 is x. Okay, so I typically call this a function h, just to simplify the notation. So this is a nice symmetric definition. Maybe the definition that is better in computations is when we eliminate one of the variables. So this is infimum of f of y plus g of x minus y, infimum of y. Okay. So what are the points where the infimum occurs? These are the critical points of this function. So if you differentiate it, you're going to get f prime of y equal to g of prime of x minus y. So if the infimum is attained, it occurs right there. And one can try to solve it for y. And this will involve implicit function theorem, differentiating again. And if the derivative is positive, then this function is going to be as smooth as f and g. And if it's not positive, then we have a problem. Okay. Now, also, maybe I should mention that sometimes the infimum maybe is not attained at one point. That's a real possibility. So just an example, if you take, say, f is identically 0 and g is identically 0, then of course h is identically 0, and the infimum occurs at every point. But under reasonable assumptions, if you have a picture like this, then the infimum occurs at a unique point, and it makes it easier. Also, maybe I should mention that if one of the functions is 0 and the second function is not, then we have this picture when we are adding 0 and something else, and of course the outcome is we just have the upper half plane. So the regularity of G is not used at all. G need not be smooth at all. The regularity, from this sum, you cannot see G. All right. Okay. So now, so typically, it's this infimal convolution is very hard to compute explicitly. It's typically given by the implicit function theorem. The example of Bauman, which I mentioned up there, is very simple. So he starts from a sequence of numbers which converge to 0 extremely fast. He'll need to specify it later. And f is going to be just akx squared, let's say, over 2. And g is going to be x to the 4th. And so such very simple functions. And so when you try to write down this equation, or 4, let's say, then you get aky equal to x minus y cubed. So this solution, it's easy to see from the implicit function theorem. The solution is analytic. And it's a solution of a cubic equation, really. Now, but if you try to write it explicitly, it will be quite messy. So even in this simple case, the solution is actually, it's not easy to work with it explicitly. We can't. Okay? It will be horrible cubic, very unpleasant. Okay? So now, but what he observed is that if you compute the infimal convolution of this fk and gk, or gk is independent of k in this case, then this will be, so if you compute the fifth derivative of this, this will be on the order of big O of 1 over ak. So the fifth derivative is going to blow up. It will be still an analytic function, incidentally, because the solution is analytic. It will be still analytic. But it just is going to have a large derivative sort of near 0. Okay? And so what Bauman does, he just considers a sequence of such functions and patches them together. So his function f will be, so he puts this fk here, except that he kind of rotates the graph and scales it by some small constant. And then, so this is maybe a point 4 to the minus k, and then the next point 4 to the minus k minus 1. And then he puts another copy of this. Again, this is scaled by a small constant and rotated. So he just patches an infinite sequence of such things. And so here it will be infinitely smooth at 0. So that's my f, which is just patched from this fk plus 1. And similarly for j, and then if you take the infimal convolution of this f and j, the fifth derivative is going to be, well, it does not exist at 0. Okay, that's the trick. And of course, it takes some work to ensure that, to glue it together and to ensure that the function is infinity. So it takes some technique. It's sort of partition of unity type argument, except that you have to keep the function convex, which makes it a little bit harder, but not a big deal. Okay? So that's what happens here. Now, how are we going to use it? So we're going to start from this example and piece together many such examples. If you recall by that, yeah, I already erased this foolishly. So I had a statement that the Gaussian curvature has to vanish at uncountably many points. Because if it vanishes at countably many points, then we cannot have a generic non-smoothness. So what are the uncountable subsets of a circle? The simplest one is a counter set. So the Gaussian curvature has to vanish on a counter set. And the whole thing should be C-infinity. So that creates some technical issues. So the building block, we start from a hinge. Hinge is just the union of two segments joined at one point. And we want to find a convex smoothing of a hinge. So here, sort of near the endpoints, it should look like this function f, or g. Okay? And in the middle, it should be convex. This is, of course, obvious that one can do it. Now, but we need more. We want to take a countable sequence of such smooth hinges and stick them together and hope that the result is going to be C-infinity. If we hope to do so, then we need to control all the derivatives. So the hinges are going to get smaller, because after all, we have a bound on the size of a curve. So when the hinges get smaller, then we need control in all derivatives. That takes a little bit of work. So it's sort of surprising what has to happen is that the hinges will have to get flatter. But also this function f, if it's flatter, then it sort of contradicts convexity. So we have to shorten it near the endpoints to ensure convexity. And when we shorten, so we kind of run this the size of how much we shorten against the angle. And we have to prove some estimate that we can control all the derivatives. It's annoyingly unpleasant. It takes several pages for us. I'm truly surprised that it does, but it's an estimate that you have to prove. And after that, everything is very easy. Well, almost. So what we do after that, we just start from a segment. So we imitate the construction of a counter set. We start from a segment, we look at the middle, and we bend this segment in the middle, and we insert here the smoothing. Then we have two remaining pieces. We bend them. Not sure if it's such a good picture. So we go up to here, and we bend, and we insert the smoothing. And then we repeat, because of the control of the derivatives, we actually have a limit. And the limit is a convex curve. Everything works. OK. So the outcome is a convex curve, which is built out of the smooth hinges. And one can also ensure that the angle is exactly 2 pi over n for some large n. It's not a dimension, of course. And then you just stick a few such, m copies together and get a closed curve. OK? Now, we are not done yet, because, we cooked up a curve such that the curvature vanishes on a counter set, but that's not enough. Remember, that was a sufficient condition. Well, that was necessary, but it's not sufficient for non-smoothness. So we have to do a little bit more work. Okay. So when you apply the Gauss map to this curve, so we have this closed curve, we apply the Gauss map, and so we get some counter set on a circle. And what we want is that, so in this counter set, we have two kinds of points. In any counter set, we have endpoints, and we have the other points. If you have a counter set, you remove an interval, and we have these endpoints. The set of endpoints is countable. Okay, most points are not endpoints. But in these endpoints, we have control. So we have we have f here, and maybe somewhere else we have g. Right, incidentally, I didn't mention that when we insert the hinges in the counter set, we alternate f and g. Okay, so maybe at the step n, we insert f. At the next step, we insert g, then f, then g, and so forth. Okay, so what we're going to play on is that when we rotate the picture for f and the picture for g is going to be superimposed, and we get a contradiction just like in Bowman. So for countably many rotations, we get non-smoothness. These rotations come in exactly when we match the endpoints. I have countably many kind of non-smooth rotations. That's not good enough because we need uncountably many. Okay, we need a generic set of rotations. So what we prove is that if your rotation is close enough to the bad one, then the derivative is still large. It doesn't have to be infinite, but it's large. And that's how, and then by taking the intersection of all these open sets, we have a dense G delta subset. Right, so how do we get dense? Right, so if you have, okay, so, right, so there are two more issues here. One issue is that when we rotate by superimposing the endpoints, we want to be sure that we get a dense set of rotations. So this has something to do with sums of counter set. So if you have a standard counter set on an interval, say from 0 to 1, and so if you add it to itself, it's a standard fact that you get a whole interval between 0 and 2. Kind of a standard feature of a counter set, of a standard counter set. Our counter set is not standard. Our we have like a counter-like set. But still, there are some results which allow us to conclude that the sum of two counter sets is the whole thing, which allows us to conclude that when we superimpose endpoints, the result is going to be dense in the circle. That's how we get a dense countable subset. And then we kind of argue that the derivative is continuous, and we get a little bit more. Now, I should mention that in infimal convolution, it's generally not true that if you change f in C4 topology, the infimal convolution is going to change in C4 topology. So this is not true. But our deformation is very specific. And we just compute that we get continuity for our specific deformations coming from rotation. And that's why it works. Thank you for your attention.